The sun is the driving force behind all processes on Earth, be it in the ocean or the atmosphere. This driving force is evident on the Earth's surface in the form of heating and gravity. In this video, we will be looking at the various processes that the sun enables to occur on the planet Earth. Insolation can be defined as any shortwave radiation that is able to reach Earth. Most of this thermal energy is absorbed at the Earth's surface, however some is reflected back into space. It is reflected as long-wave radiation, which causes atmospheric warming and provides a stable environment to support life. Insolation is affected by a number of factors, including cloud cover, however, is always at its greatest intensity at the equator. Now we know how the Earth's atmosphere is initially warmed, we can look into the processes that occur within the atmosphere as a result of areas of warm and cool air meeting. Because insolation is at its greatest at the equator, it creates an area of warm air. This causes a convection current to form, moving from the equator and towards the poles, due to differences in density. As the air becomes warmer, it becomes less dense, and so the warmer air moves upwards towards the stratosphere. Here, the air begins to cool down and become denser than that rising from the equator, and hence moves back down towards the Earth's crust at the poles, where the cycle repeats. Atmospheric cells can be categorized into three different types: Ferrel cells, Hadley cells, and polar cells. Atmospheric cells generate areas of low pressure at the equator and areas of high pressure at the poles. This is what results in pressure systems. Air always moves from areas of high pressure to areas of low pressure, and this flow of air generates air currents, otherwise known as wind. Putting this into context, it would be expected that the convection cells that are generated as a result of these pressure gradients would run directly from the equator to the poles. However, this isn't quite the case. This is because all moving things, including water and air currents, are affected by something known as Coriolis deflection. This theory stipulates that the Earth's spin causes all moving things to deviate slightly from its straight path. In the northern hemisphere, all moving things are pulled slightly to the right, whereas in the southern hemisphere, all moving things are pulled slightly to the left. As a result, winds are deflected across the Earth's surface into prevailing westerlies and prevailing easterlies. Polar easterlies are also formed as a result of Coriolis deflection, taking effect on the surface winds in polar cells. Winds generated by pressure systems play a key part in shaping the waves of the ocean. As wind blows over the surface of the ocean, air molecules collide with water molecules and transfer energy by frictional drag. When this occurs for extended periods of time, it results in waves forming and even surface ocean currents. Waves that form as a result of wind can be defined into two main categories: capillary and surface gravity. A capillary wave are the first waves to form due to wind drag and are tiny waves at the ocean's surface. Their wavelength is less than 1.73 centimeters and have a restoring force dominated by surface tension caused by hydrogen bonds at the air-water interface. Although gravity also plays a part in pulling these small waves downwards, surface tension exerts a far stronger force on the wave. Surprisingly, it's these tiny waves that result in much larger waves, surface gravity waves. Surface gravity waves grow from capillary waves if the wind continues to blow across the water's surface, and thus allowing for even more energy transfer. As the waves grow and the wavelength has exceeded 1.73 centimeters, the restoring force is no longer so much surface tension as it is gravity. This is because at these greater wavelengths, the surface tension force is too weak to pull the wave back to a flat state. Oscillating waves, a type of progressive wave, are formed as a result of the water molecules moving forward, creating a downward pull on the crest. As the water molecules at the crest of the wave move forward, the water molecules in the trough travel backwards. This causes a circular movement of water to form in the wave known as a wave orbital. The speed that a wave is travelling can be calculated using the equation v equals the square root of gl over 2 pi tan h 2 pi h over l, where g equals the acceleration of gravity, l equals the wavelength, and h equals the height of the wave. Deep water waves, where depth is greater than half the wavelength, are dependent only on the wavelength and not the depth, so the equation can be shortened to v equals the square root of gl over 2 pi. For shallow water waves, where depth is equal to 1/20th the wavelength, the equation can be shortened to v equals the square root of gh. For intermediate waves with depth between 1/2 and 1/20th the wavelength, the full equation must be used to determine the speed of the wave. The shape and steepness of the seabed plays a key part in determining the type of breaker that will occur. Spilling waves occur on very flat seabeds and form due to the crest becoming too steep and hence spills down in front of the wave. Plunging waves occur when the seabed is relatively steep, which results in the front of the wave becoming very steep and collapsing in on itself. The final type of wave, a surging wave, occurs when the seabed leading up to the coast is very steep, and as a result the waves do not actually break, and instead most of the waves of energy is reflected back out to sea. Currents can be categorized into two different types, wind-driven and density-driven. Subsurface currents are density-driven, whereas surface ocean currents are driven by wind drag across the surface. Currents are deflected by continents, and each current bends into a loop, forming circular current systems known as gyres. The most influential gyre on the British coast is the North Atlantic Gyre. The North Atlantic Gyre propels the Gulf Stream, a western boundary current that feeds the warmer waters and temperatures into northern Europe. Ocean currents are also affected by Coriolis deflection, such as with the intensification of the western boundary currents, or more simply, western intensification. This is the process by which Coriolis deflection is intensified by the latitude of the gyre, and as a result the currents flowing in the gyre are pulled to the right. This causes the eastward flowing currents, such as the Gulf Stream, to flow more quickly and also become narrower than those that are flowing westwards. Coriolis deflection also plays a part in other ocean currents. In the centres of gyres, mounds of water form due to convergence between Ekman currents. These mounds grow until a pressure gradient forms between the top of the mound and the ocean surrounding it. This pressure gradient causes the water at the top of the mound to be pulled downwards to the surrounding water. However, Coriolis deflection prevents this from happening. As the water flows down the mound, the speed of the current builds, and as a result the Coriolis effect intensifies, and hence the water is deflected rightwards back up the mound. This causes the current to lose speed, and so the effect of Coriolis on the current is less intense, and hence the current flows down the pressure gradient again. This waving process continues, with each wave decreasing in speed and energy until eventually the force of Coriolis is equal to that of the pressure gradient and dynamic equilibrium is established. This wavy flow of water is called geostrophic flow. Density-driven subsurface currents are driven by a process known as thermohaline circulation. This is the process by which the deep waters of the oceans, greater than 1,000 meters below sea level, are transported and mixed. This process begins in the polar regions, where cold, salty water sinks as it is denser than the warmer, less salty surrounding waters. This water is known as Antarctic and North Atlantic bottom water. This cold water flows along the benthos at a very slow pace, generating a deep ocean current. The bottom waters flow into the Indian and Pacific Oceans, where it is shallower and warmer. This allows the cold, salty water to begin to heat up. The warmer water is now less dense than surrounding water and so rises to the surface. Here it travels across the world ocean back to the North Atlantic Ocean, where once again the water cools and sinks, starting the cycle all over again. This cycle is best known as the Great Ocean Conveyor Belt, and one full circuit is estimated to take 1,000 years to complete. Tides come in three categories: diurnal, semi-diurnal, or mixed. A diurnal tide is one that consists of one low tide period and one high tide period per day. Semi-diurnal tides, however, consist of 2 low tides and 2 high tides daily. Mixed tides are the most irregular of all the categories, with the tidal range between each high tide being completely variable. Tidal ranges have both a maximum and a minimum, depending on the phase of the moon. When the tidal range is at its maximum, it is called a spring tide, and at minimum, it is a neap tide. Everywhere experiences 2 spring tides and 2 neap tides every month. Tidal bulges exist as a result of 2 forces acting on the world's oceans: the force of the moon and also the centrifugal force of the Earth. This creates 2 bulges in the tide, one facing the moon and the other on the exact opposite side of the Earth. The Sun also creates tidal bulges. However, these are much smaller than that of the moon, as the Sun is much further away from the Earth and hence has a smaller gravitational pull. These bulges result in tides as the water passing through the stationary bulges rise and fall again upon exit. To explain the tides further, there are 2 main tidal theories: the equilibrium model of the tides and the dynamic model of the tides. The equilibrium model of the tides is simplified and based off of 3 main assumptions, one of which being that the Earth has no land masses and an infinitely deep ocean. The occurrence of spring and neap tides due to the alignment of tidal bulges is one that is very well explained by the equilibrium tidal theory, providing a good explanation for the systematic occurrence of these tides. However, the equilibrium theory doesn't account for land masses, and so tides predicted are not entirely accurate. So how can we better understand this? Luckily, there is another model that does account for land masses, and it's called the dynamic or real model of the tides. The dynamic tidal theory explains when land masses are introduced, the tidal bulge becomes a rotary wave instead of a linear wave, caused by Coriolis and pressure gradients moving the crest of the wave around the ocean basin. This rotary wave generates a system known as an amphidromic system, whereby the tide rotates about a fixed node, the fixed node in this case being the centre of the ocean basin. And there we have it, one very brief summary of atmospheric and oceanic processes. Thank you very much for watching.